Hi, so today we talk about inverse functions or functions that are inverses of each other. And if you think of the word inverse, you've certainly heard it before in terms of operations in math, like addition and subtraction are inverse operations, and multiplication and division are inverse operations. Now we just kind of extend that concept to apply to entire functions. So the first thing we have to get a handle on is compositions. So here's the definition. For two functions f and g, the composite of f and g is f of g of x. So it's what you get when you stick one function inside of another. And we'll see plenty of examples of this. So that notation is the one I prefer. And either way, when you say it out loud, you just say f of g of x. You can, of course, also do g of f of x. That's also a composite of f and g. You will see different notation in your book and out in the streets. So here it is. It's sometimes written with a little o. It's not an o. It looks like a degree symbol, and it means the same thing. So I think you'll see it that way on the homework. Just know that I prefer my notation because it's more clear what's happening. It's clear, I think, when you write it this way that you are, in fact, putting g inside of f, rather than if you just looked at this, you'd say kind of, well, what's that little o thing mean? So when you see the little o thing, just think it means of. Okay, so let's just practice composing functions. Given f of x equals x squared minus 2x, and g of x is x cubed minus 3, let's just compose these two things together both ways. We're going to find f of g of x and g of f of x. So f of g, again, is just what you get when you stick g into f. It's just like f of a, or f of x plus h, or f of t plus 5 or something. We're going to take the entirety of g, x cubed minus 3, and substitute it for x into this function. So it's going to go in for this x, and it's also going to go in for this x. All right, so f of g is x cubed minus 3 squared minus 2 times x cubed minus 3. So everywhere you see an x here, you just substitute all of g for that. So if that's all we were asked to do is find f of g and g of f, we could actually just stop here. We like to simplify things if we can. You can kind of get a sense looking at this that, okay, we're going to square this out and distribute this 2 and then try to combine as many like terms as we can. And just so we can see, okay, when we composed a polynomial with another polynomial, what we get is a higher degree polynomial. So when you square x cubed minus 3, you get x to the 6th minus 6x cubed plus 9. And then I just went ahead and distributed that minus 2, so it's minus 2x cubed plus 6. And then we just combine any like terms we can. These x cubed terms combine and these constant terms combine. And that's all we can do. So f of g simplifies to x to the 6th minus 8x cubed plus 15. Okay, so we composed a quadratic and a cubic, and look at that, we got a 6th degree polynomial. So let's go the other way. So when we go the other way, g of f, we're just going to take this x squared minus 2x and stick it in here. So it's going to be that cubed minus 3. Okay, so similarly, g of f is x squared minus 2x cubed minus 3. It's going to be a totally different function than f of g is, and that's usually going to be the case. So once again, I'm probably not going to show all the work, but you could certainly cube out x squared minus 2x and clean that up. Okay, new example. Just to get used to this. And this is kind of a special case, and you'll see what happens, and it's leading into what the main focus of this, which is inverse function. So we're going to do the same move. So it's x minus 2 cubed and the cube root of x plus 2. So the instructions are just find f of g of x and find g of f of x and simplify if possible. So when we do f of g, the only x we see is this one, so all of g gets substituted for that x. So instead of x minus 2 cubed, it's g minus 2 cubed, which is the cube root of x plus 2 minus 2 cubed. Now just kind of look at that for a second. Do you see what's about to happen? Obviously we're going to simplify it, but do you see what's going to happen when we do simplify it? It's going to simplify very nicely, and that is intentional. So the 2's cancel. right? And now we have the cube root of x cubed. And cubing and cube rooting are true inverse operations. So one just straight up makes the other one go away. So if you cube a cube root, you just are left with just x. Okay, so that worked out well on purpose. Now let's do g of f. So do the same thing. You can probably pause the video and just go ahead and do g of f, and spoiler alert, you're also going to get x when you do that. Okay, so g of f is going to be the cube root of this whole thing, x minus 2 cubed plus 2. Right, and now again, just kind of look at it. The x minus 2 is being cubed and cube rooted. So that just straight up makes each other go away. Cubing and cube rooting are inverse operations. That goes for actually any odd root. You'll see a lot of that kind of thing. So the cube and the cube root go away. And then we've got x minus 2 plus 2. And that's it, right? The 2's cancel each other out. So we're left with, once again, just x. Okay, so that is not a coincidence. That is what inverse functions do. So in this case, f of x and g of x are inverses of each other. So we say inverse functions, but it's a both ways relationship. G is the inverse of f and f is the inverse of g. Not every function has an inverse, but the ones that do share this relationship. And in fact, the thing that just happened where they both just, you compose them and they both simplify to x, that really is one way to define the inverse. Just basically, if this happens, the functions are inverses. Okay, so that's our big vocabulary word. So it's extending the idea of inverses past just operations and into actually entire functions. But we have to be very specific now because, as you know, functions have things like domains. And they have to do things like pass a vertical line test. So we can't just go through like everything and say, okay, here's the inverse of everything, because it's very limited. So you should absorb that definition. On the test, I'll probably throw two functions like this at you and say, okay, verify that f and g are inverses using the definition of inverse functions. And this isn't the only way to define inverse functions, but it's the kind of the main way. So this is what I mean by using the definition. This is really the definition you should absorb and memorize. They're inverses. If you compose them either way, it just simplifies to x. Now, usually if it goes one way, it's not going to go the other way. It would go the other way as well. You'd have to get pretty tricky to see one that worked one way and not the other way, but it could happen. So we do have to do it both ways to verify that, yeah, these are indeed true inverses of each other. Okay, so circle that, highlight that. You're going to want to memorize that definition. So a little bit with notation. This isn't notation I love. In fact, I don't like it at all. So when we say the inverse of a function f of x, the way we denote that is an f with a little -1 in superscript. Here's why I don't like this. You have been taught correctly that a little -1 as an exponent has a distinct meaning. We've seen negative exponents. X to the -1 is the same thing as 1 over x. So like 3 to the -1 is 1/3, and that's completely correct. So if you just looked at this and I didn't tell you what it meant, you'd probably think that this was an exponent of -1, and it meant to take the reciprocal of f, which would be a wonderful guess. But in this case, that's not what it means. So when you see this, I know it looks like an exponent, but it's not. It's not an exponent. It's just the notation we have for the inverse of f. We're stuck with it. I can't do anything about it. I would come up with better stuff, but no one would listen. So if I ask you from now on for the inverse of f, I can just ask you for f inverse, which is what this means, rather than just writing the inverse of f or saying g is the inverse of f. So just to be perfectly clear, that does not mean that. You'd think it would, because that's how an exponent of -1 works, but you'll just have to take my word for it that this is not an exponent, even though it looks like one. We don't like in math when the same notation means two different things, right? And that's why we don't really like this notation, but again, we're stuck with it, okay? So do not flip it over. That is not what that means at all. So let's just look at some common inverse functions that we know. We've seen inverse functions like our whole time we've been doing algebra. We just may not have referred to them as that because, again, they just have a real specific kind of definition. But we've seen them. So we've already seen the cube root function and the cubing function are completely perfect inverses of each other. One just makes the other go away. And down the road, we'll get a couple restrictions for which functions are allowed to have inverses and stuff. These totally fit the bill and they work fine. So these are the classic inverse functions of each other. And that actually goes for any odd root and odd power. So if you had x to the 5th or 7th or whatever, and then you had the 5th root or the 7th root, those would qualify as well. So for like something like this is just a linear function, but I just want you to think about it. So this is 2 times x. What's the opposite of taking x and multiplying it by 2? Well, what's the inverse of multiplication is division. So if you're thinking, shouldn't the inverse of that just be x over 2 or x divided by 2? Absolutely, that is. So those are true inverse functions. And that goes for any linear thing. Just a constant times x, you just divide it by x and you have an inverse. Same thing with x plus a constant. You might think, okay, if I just subtracted 2 from x, would that qualify as an inverse for adding 2 to x? Yes, it would. And if you tested that using the definition we just said, well, just look at it. If you took 2x and composed it in here, you'd have 2x over 2, which is just x. If you took x over 2 and composed it in here, you'd have 2 times x over 2, which is just x, right? So it works. And this works as well. You just get x plus 2 minus 2, which is just x. Every linear function has an inverse. We'll see how to find that, but for now, you'll just have to kind of take my word for it or check it. If you plug f into its inverse, you get 2x minus 3 plus 3 over 2. The 3's cancel out, then you have 2x over 2, and you have just x. And if you were to do it the other way, the same exact thing would happen. So this is just a line, right? Mx plus b. This is also just a line, and those lines are inverse functions of each other. Okay, so let's show it. So like I said, just compose one into the other. And when I say on a test or whatever, show that they're inverses, this is what I mean to do. Right, when you stick g into f, just this replaces this x. So you get 2 times x plus 3 over 2 minus 3. This 2 cancels this 2. So the parentheses go away. And it's just x plus 3 minus 3, which is just x. And if you do it the other way, you get, okay, now this goes in for this x, so it's going to be 2x minus 3 plus 3 over 2. The 3's cancel out, as you can see, and then the 2's cancel out. You can see it's about to happen. All right, so get used to that move. Now we have to talk about graphing inverses and actually finding them, which is its own thing. All right, new word, new vocabulary term. And that is one-to-one. So there's a couple different ways to define this, and there's more mathematical ways than I have it here. But this is basically, they're all saying the same thing, and this is what they're saying. A function is one-to-one if every input has a different output. So we have to kind of think about this. To be a function, it has to pass a vertical line test, which means no input has 2 different outputs. To be a one-to-one function, now we're saying that actually every input has to have a different output as well. So like the classic one-to-one function is x cubed. X cubed is one-to-one. Think about what happens when you cube a number, like 2 cubed is 8. Well, what's negative 2 cubed? Negative 2 cubed is negative 8. And those are 2 different numbers. And to be one-to-one, that has to happen for every pair of numbers. No 2 numbers can be sent to the same function value, and I'll show you plenty of examples. So graphically, the easy way to tell if you're just looking at the graph of a function is that it actually passes. So we've seen a vertical line test for determining whether a graph even is a function at all. If you hit it with a horizontal line test and it passes, then it's actually one-to-one. So remember the test. Now, so if you run a horizontal line anywhere on the graph, it will only ever intersect once. If it intersects more than once, it's still a function, but it's not a one-to-one function. Right, so here are some one-to-one functions, and just picture using the horizontal line test on here. Now, I know in the case of x cubed, it looks like it has a flat spot here, but we kind of know that functions don't ever really flatten out like that and become constant. So it is still increasing everywhere. It's still increasing in that spot that looks flat. So just right, if you hit a horizontal line anywhere through this, it would only ever hit once. And that's because, algebraically, if you cube any two numbers, you'll get a different number. If you cube 3, you get 27. If you cube -3, you'll get -27. That goes for these other ones too. So a linear function like this is also one-to-one, unless it's horizontal. So just think about that. Like if you multiply any number by 2, you're going to get some completely different number than if you multiply any other number by 2. And that's why the graph looks like that, and that's why it passes that horizontal line test. Same with the cube root of x, so you know that that's the inverse of this, but just notice that the graph does the same thing. It never overlaps because every number has a different cube root. Now, again, it looks vertical here, but we know that functions don't really go vertical because then they wouldn't really be functions. Okay, every number has a distinct cube root from any other number, so that's why the graph looks like this, and that's why it's one-to-one. So they're one-to-one because of the algebraic operation that created the graph, not really because of the graph. That's just a way to see it. Okay, and here's the classic not one-to-one function. So this is our classic x squared parabola, right? We've seen it a million times. We know it, we love it. But if you tried to hit it with a horizontal line test, it would intersect the parabola twice. Pretty much everywhere except here, but it doesn't have to be, the horizontal line test says you have to be able to do it anywhere. And so again, the reason for that is because if you square two different numbers, you can get the same number. 3 squared is 9. -3 squared, also 9, right? That's why the graph is even. The graph is symmetrical because squaring has that symmetry. When you square 2, you get 4. When you square -2, you also get 4, right? So think about that. This is an even function. An even function could never possibly be one-to-one, right? Because by definition, it has that horizontal overlap. And you'll see any even power of x does that same thing. X to the 4th or x to the 6th or whatever is still a parabola. It's just a skinnier one. So a parabola by definition fails the horizontal line test, so it's not one-to-one. And then you'll notice when I was up here showing like common one-to-one functions common inverse functions that we already know about, I skipped x squared, even though it's a very common function that we know about. Okay, there's a reason for that. And the reason for that is this. The only functions that have inverses are one-to-one functions. So those are the only ones we're going to deal with for right now. We're not even going to try to find an inverse for x squared. If you're kind of thinking like, isn't it the square root function? The answer is yes, you're kind of right, but we have to apply some restrictions, and we have to be really careful before we do that. Basically, we have to chop this function in half. We'll get to that at the end, okay? So here's that other more mathematical definition of it. If A is not B, f of A can't be f of B. So once again, think about this in terms of squaring versus cubing. If you're talking about cubing, if for two different numbers, like 2 and -2 or whatever, those are different numbers. And when you cube them, you get different numbers, right? If you cube 2, you get 8. If you cube -2, you get -8. So that's all this is saying. Any two numbers are going to output two different numbers, right? Two different inputs have to have two different outputs. So contrast that with squaring. You can have two numbers that aren't equal, like 3 and -3, but when you square them, they give you the same exact output. So that means that squaring is not a one-to-one operation. Right, so no two numbers have the same cube, unless they're the same number, but no two distinct numbers will ever have the same cube, or cube root, or any of the other stuff we've talked about as being one-to-one. So there's a very kind of pleasant symmetry that happens when we look at graphs of inverses, when we compare a function's graph with the graph of its inverse. And here's why. Yet another way to define two inverse functions is that if f of a equals b, then g of b equals a. In other words, if f takes a and sends it to b, g, or f inverse, or whatever you call it, is going to take that same b and send it back to a. Just think again about cubing and cube rooting. If I cube 2, I get 8. If I cube root 8, I get 2. Right? So all those coordinates just switch places. So the fact that all the coordinates just switch places, all the x's and y's switch places on the graph, means the graphs really have the same shape. It's just reflected in kind of a unique way that we haven't seen yet. Like that. Okay, so there's the green curve is the cube root function, and the green curve is cubing, and the blue curve is the cube root function. The picture is right. So notice that they kind of have that same shape, that cubic style shape where it goes up and then has a little flat spot and then just keeps increasing. This one goes forward, has a little flat spot, and then just keeps going to the right. And the reason that is because of this definition. So since the point 2,8 is on the graph of x cubed, the point 8,2 has to be on the graph of the cube root of x. Since the point -2, -8 is on the graph of x cubed, the point -8, -2 has to be on the graph of the cube root of x. And that goes for every single point along this curve. So every single point along this curve has a mirror point. It has like a mirror image point on the graph of its inverse. That's why they have the same shape, just reflected in this way. And specifically, they are reflected about a diagonal. And we'll see that with everything we look at. If you have a function and you find its inverse, or you're given its inverse, you will see this phenomenon. You'll take the curve x cubed and you'll reflect it about this diagonal. So everything flips over this dotted line. And that's why the inverse has the shape that it does. That's why it has the same shape, just once again kind of reflected it in this new way. So this is kind of one way to check and make sure that functions truly are inverses, is just to make sure that they look right. Here's another example, just to get used to this kind of look, this kind of symmetry. We have x to the 5th plus 4. That is a 1-to-1 polynomial. Once again, notice odd type polynomials like this tend to be 1-to-1. So it's the same shape as a cubic, just a little skinnier, and then shifted up 4. And here's the function, the 5th root of x minus 4. We'll talk about how I found that. You'll have to find this inverse algebraically. But just given it, you can kind of see this pleasant symmetry. They have the same basic curve shape. It's been flipped over this diagonal line. So it's been mirrored in this kind of pleasant way where you can just kind of see that they do have the same shape, right? Because every point on here has a corresponding point on here where the coordinates are just flipped around. So here's a fun example that I can and will put on the test, is I could just give you the graph of a function, a 1-to-1 function, and I could not even tell you what it is, but I could say draw its inverse. So whatever it is and whatever its inverse is, you can sketch what it should look like. And we use this idea of these sort of mirror points, the fact that they all have these like twins on the other curve. All right, so take a second to draw this curve. Notice that it only goes from 1 to 5. So assume it just stops here. So it's a tiny little function, but it is the graph of a function, and it is the graph of a 1-to-1 function. It just has a very limited domain, just from 1 to 5. So if you're thinking, wow, it looks like a square root function, well, it is kind of. But either way, I didn't tell you what it is, and we just want to carefully draw the inverse based on just what we have. But we're going to use that principle that every single point on here has a corresponding point on the graph, on the inverses graph. So if you're kind of picturing what it should look like right now, I'm kind of mousing over what it should look like. It should look like that, but we want to draw it very carefully. So the first thing to note is just that we can see some points. So the 3 points that look like we can see them pretty clearly are here, here, and here. So let's mark those points. We got the point 1, 0, the point 2, 1, and the point 5, 2. So now we get 3 points on the graph of f inverse. Since the point 1, 0 is on this graph, the point 0, 1 is on this graph. Since the point 2, 1 is on this graph, the point 1, 2 is on this graph. So mark those. 0, 1, 1, 2, and let's see, since the point 5, 2 is on this graph, the point 2, 5 is on this graph. Okay, so for free, we get 3 points on the graph of the inverse. 0, 1, 1, 2, and 2, 5. And right from there, you should be able to kind of picture exactly what that other curve should look like. So we're going to plot those points, and we're going to draw this dotted line just to do the mirroring. Maybe you don't have to draw this dotted line, but I would. Remember how it's reflected. It's reflected about this diagonal line. Obviously on the test it'll be on graph paper and stuff, and it'll be easier to draw than it is just in your notebook or whatever right now. But right, we're going to reflect it about this dotted line. And we're going to make it go through those 3 points. And then it's just going to stop. So just like this curve just kind of stops at 5, 2, this curve is just going to stop at 2, 5, right? And it's going to stop right here at 0, 1. So it's just going to go between these 3 things, and I'm like highlighting it right now, and you can just go ahead and draw it, right? It should be the mirror shape of that. So it should look like kind of like half a parabola. Okay, and that's a perfect little drawing. So it should be pretty perfect when you sketch this, because like I said, you have the points and then you really have the shape too. You know what it should be shaped like, right? So it might not be computer perfect, but I will say draw it carefully on the test, and I want you to draw it carefully. One other thing I want you to notice while we're on this topic is that this function, the domain of it goes from 1 to 5. The range of this function goes from 1 to 5. The range of f goes from 0 to 2. The domain of f inverse goes from 0 to 2. In general, that's always the case. So the domain of f becomes the range of f inverse. That'll come back a little later. And it just happened naturally by the way we drew it. We didn't have to know that to draw it, but think about it. All the x values of f became all the y values of f inverse, right? They switched places, so that's why that happened. And then the same thing happened with the range of f and the domain of f inverse. All of the y values of f, which is everything from 0 to 2, became all of the x values of f inverse, which is everything from 0 to 2. Okay, so don't think about that as a fact you have to memorize. Just think about it as a phenomenon that kind of helps us a little bit down the road. All right, so this is the last thing. We want to be able to find inverses algebraically. So I'm going to give you f, and I'm going to say find f inverse. Everything so far, I've just given you a function and its inverse, and we've verified that they are inverses, and we've drawn its inverse and stuff. So we've sort of found it graphically. Now we're going to find it using, the name of the class, algebra. So let's just jump right in with an example. This function f of x is 2 minus 4x over 5, and I want you to find the inverse of this. So you're going to have to take my word for it that this is a one-to-one function. I wouldn't try to trick you with that. It's a linear function. It's just written kind of weird, but this is the graph of a line. You could rewrite it in mx plus b form if you wanted, but you don't have to. You don't really even have to know what it looks like to do this. Just trust that, yes, it is a one-to-one function, so therefore it does have an inverse. So there are a couple different ways to do this, and different books might explain it a little bit differently, but it's basically a 3-step process, and no matter how you do it, you end up in the same place. So this is how your book gives, this is like the algorithm your book gives you, and I'll stick with it because it's good. So it's a 3-step process, and here we go. So the first step is just, instead of writing f of x equals 2 minus 4x over 5, just write y equals 2 minus 4x over 5. So that's not even really algebra. Just write it as y instead of f of x. You know that those two things are usually pretty much interchangeable. All right, so just rewrite the problem as y equals 2 minus 4x over 5. So now what we want to do is we basically want to rearrange that entire equation. And you've done stuff like this. We want to solve this equation for a variable. The equation is already solved for y because we have y on one side. Now we want to move everything around so that it's solved for x. But before we do that, right, don't go nuts doing that just yet. The second step is, well, you'll see. We're going to exchange the y and the x. So we're going to take the x and the y and just literally flip them around. If that seems weird, you'll probably see why in a second. Okay, so just flip them around. So instead of y equals 2 minus 4x over 5, write it as x equals 2 minus 4y over 5. Right? So now, again, we want to rearrange that entire equation. And we want to rearrange it in a way that now we solve it for y. So that's the same thing as if you just would have dove in and solved it for x here. You'd end up doing the same exact moves. It's just that now once we do that, we once again just have y equals some function of x, which is what we want, and we're done. Okay, so again, this is just kind of the order of the book, the process from the book, and I like it, so stick with my process. Okay, so now comes the actual algebra, right? Solve that equation for y. So that's a three-step thing. We want to get y by itself, so just think order of operations. This divided by 5 is happening to everything, so we have to multiply by 5. So multiply both sides by 5, and we get 5x equals, when you multiply this side by 5, it just cancels this 5. So that's a good move to know, is if you just multiply by a denominator, then essentially the denominator just lands on this other side because it gets multiplied and then it gets canceled over here. Okay, so just take a second, if you don't believe me, to convince yourself that that algebra move I just did is a legit move. So I just multiplied both sides by the denominator. Okay, then two more moves. We're going to subtract 2 from both sides. So 5x minus 2 equals negative 4y. And then all we have to do is divide both sides by negative 4. And we're basically done. So we have 5x minus 2 over negative 4 equals y. Okay, so that's the inverse function. We can write it a little bit neater, and we want to call it f inverse, right? We don't want to leave it as y. We were asked to find f inverse, and that's it. F inverse is 5x minus 2 over negative 4. So let's simplify that a little bit by just dividing the 5x and the minus 2 by the negative 4. And I just turned the equation around because I like the way that looks better. So we have y equals negative 5/4 x, and then the negative 2 over the negative 4 give you a plus 1/2. You wouldn't have to do that. If you left it here, you'd be totally fine. But if you wanted to graph it in your calculator or whatever, then now you can see it's mx plus b, right? It's a line with a slope of negative 5/4 and a y-intercept of 1/2. All right, and that's the inverse function. If you were to graph this line together with this line, it's not as obvious when it comes to lines, but you would still have that symmetry that we wanted. And to check these, you can use the definition of inverses. You can stick this into here. So you can replace the x, right? You can find f of f inverse because that should cancel everything out and become just x. So let's do it. So f of f inverse is 2 minus 4 times all of this over 5. Right? 2 minus 4 times negative 5/4 x plus 1/2 all over 5. You can kind of see what's about to happen. When you distribute this negative 4, this becomes a plus 5x, and this becomes a minus 2. And then the 2 cancels the 2, and the 5 cancels the 5. So I'm going to let you fill in the algebra work there because it is just cleaning up an algebra. And if you get to here, you don't have to also do f inverse of f. You can if you're really thorough, but you're pretty sure you're right because everything in this one canceled out everything in that one, so they're inverse functions. Okay, and I'll do a couple more of these because I know this is kind of a tricky process. Okay, so same exact steps, same exact thing for f of x equals 2x to the 5th minus 1. So just start it off by doing the same 3 steps as before. Replace f of x with y. So we're going to have y equals 2x to the 5th minus 1. Oh, that's what the graph looks like. That's 2x to the 5th minus 1. Once again, it's a odd looking polynomial, not odd like unusual, but literally odd like 5 is an odd number. And it is 1-to-1. I know it looks flat here, but it's not. This is a 1-to-1 function, so it has an inverse. And right away, kind of start picturing what its inverse should look like. It should have this kind of shape, like a 5th root, which is exactly what it will be. Now, I'm not going to write all the steps out again. We're just going to do them. So y equals 2x to the 5th minus 1. Swap x and y. So it's going to be x equals 2y to the 5th minus 1. There you go. And solve that thing for y. Okay, so now that's really just a 2-step process. three-step process. So first add 1 to both sides. X plus 1 equals 2y to the fifth. Divide both sides by 2. X plus 1 over 2 equals y to the fifth. And then if you want to get rid of a fifth power, you know that you need a fifth root. So you just use a fifth root on both sides, and that just makes this exponent of 5 disappear. The fifth root of x plus 1 over 2 equals y. Okay, that's it. That's the inverse function. So we have two ways we can confirm that. We can do the algebra. So it's always nice at the end to write it as f inverse. Although if you just left it like this, I suppose I'd mark it right because at least you found it. So just write it. Okay, I found f inverse, and it's the fifth root of x plus 1 over 2. So to check that, again, you can stick that into here. You can do 2 times the fifth root of x plus 1 over 2 to the fifth minus 1. Everything will cancel everything. The fifth root will cancel the fifth power. The 2 will cancel the 2. And this minus 1 will cancel this plus 1. Do it if you don't believe me. I would encourage you to do it because it's a good check and it's just good practice. Or we could throw the graph up. There it is. The red graph is the inverse function we just found. Notice it has that kind of pleasant symmetry about this diagonal that I'm highlighting here, right? So it's mirrored over that diagonal, and it is the same shape. It's just flipped around and mirrored. Okay, so 2 ways to check it. I'm not going to do it algebraically again, but I am going to encourage you to. New one. This will be a little bit different. So for f of x equals square root of 3x minus 4. So this is a square root function. We haven't really seen this kind of thing, but it is 1-to-1. Square root functions are 1-to-1, right? They pass the horizontal line test. Therefore, it has an inverse. So let's figure out what it is. Same process. Just go y equals square root of 3x minus 4. Swap x and y, and then solve it for y. I would encourage you to pause the video and just try that yourself. You'll get some sort of quadratic thingy. Okay, so if not, I'm gonna do it now. Right, so a good kind of cautionary thing. We don't have to do this, but I want us to kind of, this is going to come back at the end. So let's just note the domain and range of the thing we're looking at. The range of it is only positive numbers. If you just look at the range, the function starts here and then goes up forever. So the range is just 0 to infinity. The domain we have to kind of find using a little bit of algebra. So remember, with square root functions, we have to ensure that what's under the radical is non-negative. And you can kind of see that it starts at like 1 point something, right? So we just have to figure out 1.1. So solve that for x. 3x is greater than or equal to 4, then just divide both sides by 3. And that's the domain. The domain is x is greater than or equal to 4/3. You could write that in interval notation, but we're just making a note of it for later. So, and okay, so 4/3 is 1.3 something, right? So that seems right. All right, and then the range is just positive numbers, so 0 on up. 0 to infinity for the range. Okay, so just put a pin in that. That's not going to affect what we do right now, but it's going to come in handy at the end. Okay, so let's do the algebra. Replace f of x with y. Swap the x and the y. Solve that for y. Okay, so to get rid of a square root, you need to square. So square both sides of that to get rid of the radical. You've seen this before. We get x squared equals 3y minus 4, and then just keep going to get y by itself. Add 4 to both sides. We have x squared plus 4 equals 3y, and then divide both sides by 3. We have x squared plus 4 over 3 equals y. So that's like, well, I mean, that's a parabola, right? It's a squaring function. If we write it a little differently, I'm just going to once again just take the 1/3 and distribute it to both terms. So it's f inverse is 1/3 x squared plus 4/3. You can kind of see what it is. It's a parabola that's been shifted up. So shifted up by 4/3. and then actually vertically kind of vertically shrunk by a factor of 1/3. So we talked about vertical stretches and shrinks. They're kind of hard to graph, but just we know what it is. This has been shrunk. So it is just a parabola. But we have a little bit of a problem with this type of function, but I'll show you how to fix it. So here's the graph of that parabola. And a parabola, or a quadratic graph, is not 1-to-1 at all. So this actually isn't quite right. This cannot be the inverse function of this, because by definition, to even have an inverse function, this new thing would have to be 1-to-1, and it's not. Okay, so this isn't quite right yet, but we're going to fix it. So really, it's this stuff back here, right? So it's not 1-to-1 now, but it's this stuff back here that's making it not 1-to-1. So just visualize chopping this stuff back here off, okay? We can do that. Like, this is math. We can do anything we want. Nobody gets hurt. So by chopping this part off, the technical term for that is restricting its domain. Now, we restrict the domain of this quadratic so that x is greater than or equal to 0. Visually, all that means is that we're chopping off the whole left half of the parabola. Once we do that, you will see that it looks perfectly right. And then I'll say, okay, but how do we know to do that? There's a way to know to do that. But basically, if the graph you get isn't 1-to-1, you have to make it 1-to-1, or else it's not a true inverse. All right, so now it looks right. Right, visually we should know what they're supposed to look like. But now our green function, our parabola, or half a parabola, is in fact 1-to-1 because we just chopped half of it off. And really for this class, that's all restricting a domain is ever going to be, chopping off half of a parabola. You'll have to do this again when you look at trig functions, because trig functions are super not 1-to-1. So here's the actual inverse. So the actual inverse function isn't quite this, because this isn't 1-to-1, it's this. So when you want to restrict a function's domain, you just put a comma after it and then just say, okay, but only for x is greater than or equal to 0. And that does it. So this gives you this graph. Might be kind of tricky to graph that on your calculator or something, but in math, you just give a function, and if you want to chop off part of it, you just clarify which part of it gets to be in. It's like an if statement for computer people. If x is greater than or equal to 0, then the function is this. If it's not, then it's just not, and you just don't see it, okay? So now it looks like a true inverse. Sorry, that moved. So one thing to note, again, is that the domain of our inverse, how did I get that? I mean, I just kind of looked at it, but how can I always get it? I make it the same as the range of f. So that's why we noted this originally. The original range of f, the purple thing, was just y is greater than or equal to 0. So if you just match the domain of the new thing to the range of the original, then it works perfectly, because remember, the domain and the range switch places, okay? So if you're wondering how to restrict the domain of the new one, if you even have to, then you always just make it match the range of the original. And this just happened because we did it right, but the range of f inverse is, it looks like it starts at 4/3 and goes to infinity, which is exactly right. It's the same as the domain of the old one. So that's, for this kind of stuff, that's the cardinal rule to keep in mind. In general, the domain of the original function becomes the range of the new function, and vice versa. But really, it's this second one that you might have to worry about. The range of, the domain of f inverse is always the same as the range of this one. It's just, it involves x, whereas range involves y, but it's the same. It's just, it's greater than or equal to 0. So that matches that. The x and y values all switch places. That's just another way of saying that the domain and range switch places, and that's why the graph looks the same as this graph, only reflected. All right, last problem. So if we ever want to find an inverse for a function that's not 1-to-1, we have to make it be 1-to-1. And like I said, this will come up in trig a lot, because trig functions are waves like this, and waves are very much not 1-to-1. So you will have to invert them. But to do that, you'll have to restrict their domain. So there's lots of different ways to restrict a function's domain. We just want to do it, in this case, in a sensible way. And we can always do that. Again, it's math. You can just chop off half a function if you feel like it. All right, so let's do an example. So notice we haven't done the inverse of any parabolas. And we know why now, because they're not one-to-one. They never are. They're symmetrical. Okay, so let's do it anyways. So this example, f of x equals x plus 2 squared. It is not one-to-one, okay? But we can make it one-to-one. And again, like, there's a lot of ways to do it, but let's do it in the simplest way possible. Let's just look at this parabola and chop half of it off. Which half to chop off? I don't know. It always seems more intuitive to me to chop off the left half. You could chop off the right half too. But I think in general, a good rule is just chop off the left half. That way we have this part of the graph still. Okay, so you can just look at it and see where to cut it now. If we just cut it right at, this is called the vertex, just cut it right at the vertex and just take everything back here off. So you can see that since, okay, we know that this was shifted to the left too. So if we just start it at -2, we will have a one-to-one function. So this part's going to be up to you. All right, so if we chop it right at -2, this new thing is. So really, just think about, for the exam, it's going to be a parabola, probably. And to restrict a parabola, just chop it right off at the vertex. So chop the left half off, figure out where the vertex is. And this new function, f of x equals x plus 2 squared with its restricted domain is one-to-one and therefore has an inverse. And now we don't have to worry about this anymore. Like, we won't have to go back in at the end and mess with it. You'll see. So now we just go charge ahead and just find f inverse. So I didn't say that's what we were doing, but that is what we're doing. We are finding the inverse function for our new restricted parabola. Okay, so let's do it. So write y equals x plus 2 squared. Again, you don't really have to worry about the domain anymore, so you don't have to write it every time. You'll see. And then just solve that. So now we have to square root both sides of this equation. You hopefully know that when you square root both sides of an equation, you have to include a plus or minus, but that won't be an issue here because we chopped this function in half. So you can go ahead and just not do that for these problems because it's only half a parabola. All right, so swap x and y. X equals y plus 2 squared. Solve that for y. First step is to square root both sides. In this case, you don't need a plus or minus because this is really only half of a function, so that won't be an issue. So it's going to be square root of x equals y plus 2. And then you just subtract 2 from both sides. And that's the inverse. Let's look at that and make sure that, like, all our domain and range stuff works fine. All right, so the inverse function of our restricted parabola is just straight up square root of x minus 2. There it is. You actually know what that looks like. It's just a square root function vertically shifted down 2. So it starts there, right? Since this one started at -2, 0, this one starts at 0, -2. Has a kind of pleasing symmetry like that. And if you just look at it, well, the range of this one is 0 up to infinity. The domain of this one, the domain of this one is 0 up to infinity. The range of this one was 0 up to infinity. The domain of this one, since we chopped it, was -2 up to infinity. That means that the range of this one is -2 up to infinity. But it is automatically. We didn't have to do anything to make it like that. It just worked out fine for us. Since we properly restricted it in the first place, they just switch places automatically, and you're just done. So that's it. That's the inverse. Okay, I'm going to do one more. If you're tired of this and want to stop the video and try the homework problems, I would encourage you to go for it. But since this is the last thing before the exam, I'm going to do one more. So you can pause it here and come back to it if you want another example, or if you want to do one, we'll just burn through this one just so that you have one more, okay? All right, so we're going to find f inverse for f of x equals square root of x minus 1 plus 2. It's going to be kind of similar to a couple problems ago. The inverse function we get is going to be a parabola, and then if we just chop that parabola in half, we will be totally fine and we will have a true inverse function. So if you're feeling good, just pause the video and go ahead and dive in. But I'll walk through it either way. So start with the algebra. Set y equal to Square root of x minus 1 plus 2. Make a note of the range. Okay, so I guess we can make that note now. The range of this thing is 2 up to forever. So that's going to be what the domain of our inverse has to be. We don't have to worry about that yet. We're just anticipating it. Swap the x and the y. Solve that for y. Notice if you solved it for x first and then swapped the x and the y, it'd be totally fine. We'd end up in the same place. So if that way makes more sense to you, totally fine, as long as you end up in the proper place. Okay, so to solve that for y, first you subtract 2 from both sides. To get rid of that square root, you square both sides. And then add 1 to both sides. There you go. So that's f inverse. You actually know what that function looks like. You actually don't need a calculator to graph this. This is a parabola shifted to the right 2 and up 1. So it's a parabola that has its vertex right here. Right? But the problem is that it's a parabola. It's not 1 to 1. So we have to just take half the parabola. All right, so we think about restricting the domain to match this range, or we think about just chopping the left hand off, the left side of it off. Okay, so that's what it looks like. So when you have x minus 2 squared plus 1 that just starts at the vertex, right? So we just took off this left half is no longer here, then it's fine. And it's a perfectly good inverse function for this square root function. So the answer in the beginning of why aren't we looking at square roots and squaring functions? Well, because we had to talk about domains. So all square root functions do have inverses. They're just restricted quadratics. And a restricted quadratic has an inverse function of a square root. Okay, so if you're going this way, that's when it's up to you to restrict the domain at the end. If you start with the parabola like the previous example, you have to restrict the domain right at the beginning. Okay, that's all. Thank you.